Okay, today we're going to start chemical equilibrium, and the whole idea here is that any chemical reaction that takes place, where you start with reactants, you know that you're going to end up forming products. Now, in a lot of reactions, especially ones that take place in the gas state or an aqueous state, the reaction is reversible. And if the reaction is reversible, that means when you have too much product, the reaction starts to go backwards and starts to break up that product and reform the reactants. This process is called dynamic equilibrium because the reactions are constantly happening. Let's say that this reaction were to take place in a flask. Well, in the flask, whatever color the solution is, if there is a color, you would not be able to see a difference by looking at it. But at a microscopic level, the reactions are still happening, the molecules are still bouncing off of each other, and reactions are still happening, right? But you just cannot see it at a microscopic level. But you might be able to see it at a macroscopic level. It depends on whether it has color or not. So macroscopic means on a large scale, like as what you can see. Microscopic means, on a microscopic scale. Either which way, the state of chemical equilibrium is when the concentration does not change. There's no change in concentration anymore. So, for example, if we look at this reaction here with the N2O4, this is a decomposition reaction. This is going to break down and form nitrogen dioxide. Now, in this situation, if we start with only N2O4 right here, so this is our initial. When this reaction starts in a flask, say we have a flask, and it's plugged with a rubber stopper. If we start with only N2O4 in here, that means this reaction is going to break down and it's going to start to form NO2. Now, as the N2O4 is being used, the NO2 starts to increase, which is why we see the NO2 here in red increase from 0, and we see the N2O4 decrease. And eventually you get to the point where both lines are flat. There's no more slope anymore. Once this happens, this is when we have reached chemical equilibrium. From this point on, the reactions are still happening, but the concentrations of both just don't change anymore. Another example here. In the second trial here, we are starting with just NO2. Right, so in our flask, you got NO2, and it's plugged. Now the NO2 decreases, and we start to increase the amount of N2O4. And so we see N2O4 being made, we see NO2 decreasing, and both get to a point where the concentrations no longer change. That's how you know you've reached chemical equilibrium. So, if you understand that, then we can start to talk about this mathematically. The ratio of the concentration of the products over the reactants can be mathematically expressed as what we call an equilibrium constant, KEQ. KEQ is mathematically determined by taking the concentration of the products at equilibrium over the concentration of the reactants at equilibrium. Right, so that's what we mean by saying ratio. And every time you see this, brackets, that's a concentration. We're going to be using molarity as our concentration, so that means you would plug in the molarity for that value. So, in the case of the reaction we just talked about, with the N2O4 breaking up to form NO2, the products are the NO2, the reactants are the N2O4. So by taking the concentration of the products over the concentration of the reactants, we get to the equilibrium expression for this reaction. Now note that the coefficient of 2 here, anytime there is a coefficient, that's going to become the exponent when you write it in the expression. For the ammonia reaction, NH3 is our product, nitrogen, hydrogen is our reactant. So our equilibrium expression here, well, pause it here and see if you can figure it out. Okay, so the KEQ value, we take the product's concentration, which is NH3, and because it has a coefficient of 2, we have to square that. And we're going to take that over the nitrogen concentration and over the hydrogen concentration. Now, the hydrogen has a coefficient of 3, so that's got to be cubed. So that's the equilibrium expression for the ammonia reaction. All right. Now, we talked about this KEQ value. We talked about how it's a ratio of the products over the reactants at equilibrium. At equilibrium. That's important. At equilibrium meaning once the forward reaction and reverse reaction are equal and the concentrations no longer change. Well, the number itself of KQ has meaning. And what it means is that if it's a large number or a small number, that tells you what there's more of at equilibrium. So, for example, if K is less than 1, that means it's reactant favored at equilibrium. Okay, so that means on a graph of reactants versus products, at equilibrium, let's say that line right there is where equilibrium happens, there's more reactant than product. That's why when you take the ratio of products or reactants, you're going to get a small value. Whereas if K is greater than 1, it's product favored. And what that means is that once equilibrium is established, you have more products, your concentration of products is greater. So KEQ is much larger than 1. Okay. It's important to note, equilibrium constant can be changed, but only by temperature. Temperature changing is the only thing that can change the value of KEQ. Nothing else will change it. That's going to come up later. Okay, so let's take a look at this example here. We've got hydrogen reacting with iodine to form hydrogen iodide. Let's go ahead and write the equilibrium expression. So I'm going to go ahead and pause it while you write that out. Okay, so the KEQ is going to take the products, which is hydrogen iodide. We're going to square that because of the coefficient of 2 over the concentration of hydrogen and iodide. Now, the next step is to find the value for KEQ. Well, they gave us equilibrium concentrations, and so this setup is for equilibrium. We can go ahead and substitute in the values. So HI is told to us to be 0.1, and we're squaring that. And this is over hydrogen, which is 0.015, and iodine, which is 0.0135. So we can go ahead and calculate that. We get a value of 49.4. So since this value is greater than 1, this is product favored. That means at equilibrium, you're going to have more product than reactants. Okay, let's try the second scenario. For this reaction, let's write the expression. So KEQ, we take our products. In this case, the reaction is written in reverse. So we have hydrogen times iodine over the HI. The HI is still squared. So we plug in the values that we have. So hydrogen is 0.035. Iodine is 0.045. And HI is 0.280, and that, of course, is squared. So if we crunch the numbers on that, we get 0.0201. All right. This reaction, because it's got a low value of KEQ, so this would be reactant favored. Now, remember how I said that this was a reverse of the main reaction, the first reaction? So what happens if I take the inverse of this 0.0201? That gives me 49.8. Does that look familiar? So this leads us to our first law of working with equilibrium constants, is that this value and this value are the same, but in order to make them the same, we had to reverse the reaction and take the inverse of the K. So, law 1. If you reverse a reaction, the KEQ, I should say the new KQ, is inverse the previous. So in other words, 1 over 0.0201 is how we found new KEQ. All right, I know this is kind of a lot, but we're almost there. So that was law 1 we just talked about. If the equation is reversed, the new KQ is the inverse of the old. The second law is that if we multiply coefficients by some factor, the constant is raised to the power of that factor. So for example, let's say I have A plus B forms C. And let's say the KEQ is 5. Well, if I multiply this entire equation by some factor, let's say I have to double everything. So 2 times the reaction. That means the reaction is going to be written as 2A plus 2B to form 2C. The KEQ is going to be raised to the factor of 2. So therefore, 5 squared, 25. 25 is the new KEQ. So whatever value, whatever factor you're multiplying an equation by, that's the factor that you raise the KEQ to. So if this was a 1/2, then you'd raise the KEQ to the 1/2 power. If I multiplied it by 3, I would take KEQ to the 3rd power, and so on. All right, so the last rule is that you can combine equilibrium reactions, and you can produce a third equilibrium constant. So Q plus R, but that's not an R. Q plus R to form S, for example. And S forms T. So I've got these two reactions. The KQ for the first reaction is 2, and the KQ for the second reaction is 10. If I can algebraically add these two equations, if they have something in common that will cancel out when I add them together, then they can be combined. So adding these two reactions together, I have S as a product, but I also have S as a reactant. So I can combine them. So that means for this reaction, Q plus R to form T, this is the result of combining the first two reactions. And when I do this, the new KQ, so K new, is equal to K1 times K2. So in this case, it would be 2 times 10, so K new would be 20. All right, and the last concept. So far, all the equilibrium reactions we've looked at have been gases. right? So they've all been homogeneous equilibria because the state has been the same for all the reactants and all the products. Sometimes there are equilibrium where you have different states. And if you have different states, then that's what we call a heterogeneous equilibria. So in a situation of a heterogeneous equilibria, any pure solids and liquids are not included in your equilibrium expressions. And the reason for that is that concentrations do not change for condensed states. Solids and liquids are condensed states. So look in here. Water will break down, hydrogen peroxide, H2O2, hydrogen peroxide, liquid form, breaks down to form liquid water and oxygen gas. Now I've got two condensed states right here. Now normally you would write this as products over reactants, so your inclination would be to do this. But this would be incorrect because of the liquid state, which are condensed states, which means these cannot be expressed in concentrations, so they must drop out of our expression. So therefore, KEQ is just going to be the concentration of oxygen. Try the second one here and see how you do. Okay, so I've got two condensed states. My reactant is a condensed state, and one of my products is a condensed state. So I have to ignore them. I cannot use them. So I'm just going to use the concentration of the CO2, the concentration of the water. It's in gas form, so that's water vapor. And that's it. Okay, and that's all for now. Go ahead and try the first homework and check yourself against the key.